Okay, thanks for the opportunity, and I hope to keep you entertained for the next half hour or so. I'm just starting with an advertisement for an upcoming conference that we're hosting on synchrotron-based environmental science. It's in the end of September, beginning of October, and you're all welcome to attend. It's especially inexpensive for students. Okay, so I'm going to talk about some applications of XAFS in complicated and heterogeneous materials, and also at lower energies or tender energies. So I just want to kind of start off with a quote that nothing is so difficult, but it may be found out by seeking. And that's a quote from 2,200 years ago. It applies very much to XAFS and science in general. The interesting thing is that Terence was not a scientist. He was actually a comedian. But he had a good point for science. So I'm going to talk about pushing XAFS beyond the ideal applications. As Anatoly pointed out in his seminar recently, XAFS works best in simple systems where things are well behaved, primarily because XAFS shows the sum of all atoms of the target element that are illuminated by the beam. So if you have more than one species or population there, you see everything. It gets complicated. Also, hard X-rays typically range from 5 to 20 kilovolts for XAFS experiments. That's generally easier than the lower energy or softer X-rays. And data analysis software is generally optimized for transition metals. So if you push outside of those envelopes, it gets a little more challenging, but it's not impossible. Because often we want to characterize the chemistry of an element in much more challenging systems. So systems that are complex or heterogeneous materials, a lot of natural materials like asteroids, meteorites, rocks, soils, man-made materials like engineered materials or batteries can be very complicated. Also, lighter elements such as sulfur and phosphorus are important as well, and you want to be able to reach to those. Sometimes use alternate absorption edges of heavier elements as well. And oftentimes, multiple species of an element are present at the same time. So you need to be able to sort that all out. So I'm just going to kind of go through some examples and how to address these and what to watch out for and where the challenges are. So I'll describe some examples in complex materials, primarily by using microbeam XAFS. So we're looking at smaller subregions of samples, and also lower energies for sulfur and phosphorus. For the lower energy elements and lower energy edges, these edges are more sensitive to the local chemistry and coordination. The energy of the electrons is closer to the valence electron energies. So it's much more sensitive to what's going on around an atom than the harder X-rays. But there are special considerations for doing these experiments. And now I'll finish up by talking about some data handling approaches for complex cases, such as imaging different species of an element and untangling mixed spectra for XANES or XAFS. And then spectral feature analysis as a specialized tool for taking apart complicated spectra. So the first example, and anyone is welcome to ask questions at any time, so don't hesitate to interrupt. So the first example is the asteroid Ryugu. It was sampled by a space mission from the Japanese Space Agency. They went out and got samples from the asteroid, brought them back as pristine samples from the early solar system that we don't have on Earth. They brought back only 5.5 grams of material, so it's pretty precious samples. We were lucky to get a few grains. This image is a pink beam X-ray fluorescence tomography cross-section run at Ryan's XFM beamline. So it's a virtual cross-section through a grain without physically slicing it. And it reveals a complex assemblage of minerals. Across the bottom there, there's a key of what minerals are different colors. This is a selenium, iron, and manganese map of the sample. And those specific minerals were identified by microbeam XANES and XAFS to confirm what they are. But you can see it's really a heterogeneous mixture of somewhat unusual phases. And as for the identifications, some examples for the carbonates that are present there, we use calcium XANES. So you see on the bottom curve, that's a reference of calcite, simple calcium carbonate, and its structure is two peaks. Dolomite, which is a calcium magnesium carbonate, each of those two peaks is slightly split. And anchorite, which is a calcium iron carbonate, same structure for all three, but just different chemistry. In anchorite, those peaks are even more widely split. So the Zanes is quite sensitive to the local chemistry and can be used to identify different minerals in different locations in the sample. Yes, there's, in the previous slide, there's a reference, and I have a list of references I'm going to have available and posted. We also used selenium and sulfur XAFS, full XAFS, to identify the sulfide minerals that are present as mostly pyrrhotite. And selenium is a chemical proxy for sulfur in most natural systems, so you can use either one. And the selenium was easier to access inside the sample with hard X-rays. So that's a good pairing. Coming back to Earth, a group that collaborated with Ryan looked at simulated material related to the Chernobyl nuclear accident. So in that meltdown situation, the nuclear fuel, the zirconium cladding, and the concrete containment all melted into a lava-like, highly radioactive material. So this group simulated that material and characterized it by microfluorescence, micro X-ray diffraction, and micro XAFS, so that they identified different phases that formed within it, both crystalline and amorphous. And they used the XAFS to reveal local coordination of uranium in both the crystalline and the amorphous phases in this material to help understand its stability and its properties for long-term containment and eventual cleanup. And a third very different example is a study of trace elements incorporated into a single crystal of topaz. This is from a local geologic project. So we used microbeam XAFS to identify which crystallographic site, either the octahedral aluminum site or the tetrahedral silicon site, was the host for various trace elements. And interestingly, as shown here, we found that arsenic was substituted into the tetrahedral site. So it's essentially arsenate substituting for silicate, which is relatively unusual in geologic systems. We also found that manganese, iron, and gallium were substituted for aluminum, while germanium substitutes for silicon. So this was done by microbeam X-ray, microbeam XAFS, and that was published last year. So through these examples, we can identify a number of different challenges and limitations for microbeam XAFS. It's not that easy to get microbeam to behave well enough to do XAFS. Most beamlines are optimized for imaging rather than energy scanning. So combining the two usually has some compromises and some challenges. The biggest challenge is the positional stability of the beam while scanning energy. Typically, the beam will want to walk a little bit on the sample during energy scanning. For bulk XAFS, where you have a uniform sample and a big beam, that doesn't really matter. But for microbeam, it's very challenging. The greatest challenge is if there's a particle size the same size as the probe beam. If it walks the slightest bit, it'll walk off the particle, and your spectrum will do all kinds of crazy things that won't be very useful. So you have to find larger grains or more uniform areas of samples and take that into account. Make sure that you accommodate that. It's also important to think about what's behind what you're looking at. When you're looking at very small things, the sampling depth of the X-rays, especially at hard X-rays, is pretty deep. It can be hundreds of microns or even millimeters. And so you have to be aware of what's behind your sample. Thin samples are best, but even thin samples, a classic thin section is 30 microns. So you're still seeing 30 microns of material with the beam. Also, what it's mounted to is important. A typical glass slide that you might have a rock thin section mounted to, a glass slide has half the periodic table in it. So you need to use high purity glass. Otherwise, you'll be seeing all sorts of things that are not in your sample. And finally, at the microscale, many mineral grains or different materials as well are single crystals. And so the orientation of a single crystal relative to the polarization of the X-ray beam can change the shape and structure of spectra. So you have to take that into account, or at least be aware of it. So it's also important to understand more about the beam characteristics of the beam that you're using for microbeam spectroscopy. As I said, most microprobes focus on imaging, so they focus to a Gaussian spot, kind of like in this left example here. It's a nice hot spot, but it does have fuzzy tails. And even though these are small tails, they extend quite a ways out from the central spot, and even though they're weaker, you might be trying to measure something that's a low concentration of an element, but nearby is something that's a weight percent concentration of that element. So if your tails reach that, you'll be seeing that instead of what you think you're looking at. And this is more important, especially on insertion device undulator beamlines, because the high flux and coherence often creates particularly long tails in the horizontal and vertical direction, like a cross. And those can extend sometimes more than 100 microns from the central spot. And they can wreak havoc with spectroscopy if you're looking at low concentrations. So one of the things that made the test beamline at NSLS2 unique is that its optics were designed to create a sharply defined rectangular beam that had a flat-topped, basically a plateau profile, and no tails, and that it was user-tunable. So you tune it to the size of a particle to optimize it for a particular grain within a sample. And that combined with decoupling the optics from the energy scanning enabled the test beamline to measure full XAFS of a particle the same size as the probe beam, which was it was the only beamline in the world that was capable of doing this for the lighter elements. And we hope that when it comes back into operation, it will be able to do this again. So the test beamline leads us in. Oh, go ahead.
Because I think you're moving to another subject. I have a follow-up question. So, generally, probably depends on the composition. But is the beam, is the penetration depth comparable to the lateral dimension, or deeper, or smaller? If it's deeper, then you're probing something I wanted. In the sample, is it smaller or?
Okay. It's energy dependent. For hard X-rays, it's definitely deeper. So ideally, you would want the sample thickness to be the same as the lateral dimensions of the probe beam, so that you're measuring a volume of that size. As you go down in energy to the tender energy range, that gets much shallower, so that becomes much closer. So for tender X-rays, the sampling depth is a few microns generally. So you really aren't seeing much behind there. So the tender X-rays, soft X-rays are typically below 1 or 2 keV. Hard X-rays are generally above about 5. It's a debatable definition, but tender energy is somewhere in the 1 to 5 range, in between those two. And that covers elements like phosphorus and sulfur and silicon and calcium. So the lighter element Zanes is very sensitive to oxidation state, local chemistry, and local structure. As I said before. And for example, sulfur Zanes, the different sulfur species are spread out over about a 10 eV range. So it's a nice distribution. So sulfur is like one of those really great examples of how things work well. Phosphorus is a little bit more complicated. There are some lower energy reduced phases, but most phosphates are centered around this energy at 2152 eV. And there's only more subtle differences between different species as far as phosphorus goes.
One brief question.
Sure.
So are these different plots on these graphs, are they different oxidation states, or are these different materials?
And these plots, it's different oxidation states. So that's showing a bit more of the spread. But actually, for the sulfur, these two are both sulfides, so they're still different enough. And for the phosphorus, I will show examples later that show the differences of the same oxidation state. Good question, though. Silicon, again, silicon, these are all the same oxidation state, but the silicon K edge requires a special monochromator crystal to reach, but we hope to be able to do that as well. But again, it shows a lot of differences in structure, small features, peak position, with different chemistry and different structures, and also different coordinations. And for a heavier element, okay.
How much, with the softer the energy, there are people who recognize the features in people.
Yes.
Are these too hard X-ray energy for you to do that, or sometimes you can use it like silicon, different gauge, silicon yields, well, probably different L edge, right?
Yeah.
But for K edges, yields and K edges, X-ray, tempted to compare them. And you look at this.
As you get down even lower energy in X-rays, they overlap more. Not as much. There were a couple of examples, I think, but not too many. But you do people start to recognize similar features anyway when you get down to lower energies. So uranium is a good example of something with both hard X-ray and tender energy edges. So typically, uranium is looked at the L3 edge, which is shown on the left, and it shows a slight separation with oxidation state from 4 to 6. But the M edge is much lower energy, only 3.5 keV instead of 17. And it shows a very sharply defined peak that's also distinguishing between the two oxidation states. The interesting thing about this is in this plot, you can't even see the edge step, but it's really small. The peak height is about 12 to 15 times the edge step height. So it's a very much amplified peak. And so this is really good for making distinctions between uranium-4 and 6 at very low concentrations. Because we've done this down to a few ppm.
You have to use like analyzer crystals for this?
No, just ordinary fluorescence energy dispersive detector. So sometimes the lower energy edges give you more access to more details than you get at the much more broad higher energy edges. So I've used things like the zirconium L and
Right, that grade you measure. Whether it's like oil.
this is in dolomite, calcite, zirconium, and zircon and monazite.
If you know something about material properties.
Just a little bit. At the L edge, you have to worry about rubidium and strontium, which are common elements in the same samples, and they do interfere. At the M edge, the interference, the only common interference that I've run into is silver, which is relatively rare, although Troy will attest to running into that problem at some point. The samples from a silver mine.
That issue with potassium.
It's below the potassium edge, so.
Oh, I was looking at M4.
Right. Yeah, the M4 hits potassium. but the M5 edge of uranium is below the potassium and calcium edges. So two commonly very abundant elements, so you're nicely not activating them. So you're staying away from interferences pretty well.
Sorry, maybe like give a sense for rating.
They range from 30 to, though those samples ranged from 30 to 200 ppm. We've done this measurement down to about 1 ppm. I just need to, for that you need to measure a few scans. But it's really sensitive. It's such a sharp peak. And even when it's noisy, it's still unmistakable which one it is. That's the beauty of it. So coming back to the Ryugu sample, this is a surface map of the whole grain. We didn't want to cut these grains because we had to send them back. So we just, for the tender energies, again, this goes back to the sampling depth. Sampling depth is only a few microns, so we could look at the surface of the sample, the surface of the whole grain, and not worry about it. At this energy range, even a thin section of a rock material is infinitely thick to the beam. So that kind of makes it easier in some cases. So in this image, blue is silicon, so the silicates in the matrix of the material is blue. The green is sulfur, so those are the sulfide grains. And the red, there are small hot spots of phosphorus. There are some black spots showing on that, and those are carbonates that don't have any of those three elements. So typically we'd map a sample and then do the microspectroscopy at different selected locations to see what's there. It's also important to make the distinction that XAFS can identify phases of grains in samples like this that microdiffraction won't be able to resolve, because microdiffraction at harder X-ray energies will be sampling the whole thickness of a sample. So it's an advantage that spectroscopy has over diffraction in some cases. And the sulfides, we did zanes of the sulfides, and they fairly closely matched with the mineral pyrrhotite. But we confirmed that with full XAFS because there are a lot of different sulfides that are fairly close. So we wanted to distinguish that. And you see that some of the spots that we measured showed a peak marked by the arrows at a higher energy, and that indicated a partial oxidation of the sulfide to sulfate. And that probably happened by exposure to air. So it's not native to the sample. So some samples are you have to be careful of sample handling and sample preparation before interpreting what you see.
So in this case, does it matter self-absorption effect, for example? Like, is that affecting your analysis? Or
there is some self-absorption for sulfides, for metal sulfides. Typically, the metal absorbs so heavily that it reduces the amount of self-absorption. But you never eliminate it completely, and it's always a concern. And I will get to that in a bit. I have a whole slide on self-absorption because that becomes important for a lot of details. And the last one, the phosphate, all of the phosphate spots measured in this sample matched apatite, the distinctive shoulder peak for a calcium phosphate. Match there. And for phosphates, you definitely have an issue with self-absorption. So the difference in the height of those peaks is some degree of self-absorption. Actually, in the standard, not in the. No, it's in one of. It's in one of the samples, not the standard. So you have to be careful of self-absorption. Coming back to Earth, literally. Phosphorus and sulfur XAFS is a really useful tool for soil science, soil chemistry. You see, this is a typical soil on the left. It's got a lot of distributed sulfur compounds and also a lot of phosphorus hotspots with different appearances. Some appear to be coating grains, some appear more diffuse, some appear more distinct. The more distinct ones, like the one labeled 2, that's a spectrum that shows it's the mineral apatite. And the phosphorus speciation is important because it's an important nutrient for plants, but it's also, if it washes out of a soil into surface water, it can damage water quality, have algae blooms, be a pollution problem. So its behavior depends on its speciation. So you really want to know what it is at the microscale. And what's present in the bulk amount of phosphorus present in the soil usually doesn't tell you anything about what its properties will be. That depends on the local speciation. So the grain mark 2 is the mineral apatite, so it's a mineral grain, so it's relatively inert, and it will not be bioavailable, and it won't wash away very easily. But the one labeled 1 is more diffuse, and that's actually phosphate adsorbed to ferrohydrite, an iron mineral. And you can see that there's a characteristic little pre-edge feature that's characteristic of iron 3+ phosphates, not iron 2+ phosphates, so it can actually tell the difference of that. But this form of phosphate is easily released by redox-driven processes. Plants can access it for a nutrient, but it can also be released by redox-driven dissolution of the iron mineral that might happen during flooding or during sea level rise. So it's sensitive to changes. So it's important to know what the distributions of those are within a soil sample. And so the inset here actually shows some of the variations in phosphorus zanes for different phosphorus mineral species. And unlike the sulfur, where it's really spread out, these are pretty subtle. So you just see small shifts in the main peak position, or shoulder peaks, or pre-edge peaks, different features like that. So those are distinctive and still allow you to identify different phosphate species, but you have to look a little closer. No, we would typically we'd map a large area at 5 or 10 micron resolution. Then regions that were more interesting, we'd map at 2 to 4 micron resolution, get more detail, and then go into places within that map to get point spectra. You have to go back to do the mapping at an energy above all 3 elements, and then do the zanes at an individual pixel of the map by scanning the energy. We've tried a couple of cases where you scan the energy and get a pixel, get a spectrum at every pixel. It takes forever, and you get a lot of spectra of things that you don't want. So it's much more effective and efficient to map the pick spots and then do the point spectra.
Sure. So the fluorescence, people usually use it for that, right? The elemental information. Can we also say that in light elements, the reason why absorption, the energy depends on the chemical environment, fluorescence also makes. People observe changes in the fluorescence. Or magnet, like when you do magnet, you don't lose control. But you can still resolve the fluorescence emission line.
Right. So the fluorescence emission lines, they may change very slightly with chemistry, but not within the resolution of the detectors used for this. You would have to use a much higher resolution detector.
It does, and it's also the chemical and structural.
I believe that has been done for sulfur in a couple of special cases, using a high resolution detector. But typical fluorescence detectors don't have that resolution. But there's another approach to that we can use that I'll get to in a few minutes. This is an example of from battery science, so the battery people who are here. In this case, we used sulfur microbeam XAFS to find just the right spot within a very heterogeneous sample to get the data that we needed for this paper. And it captured the localized formation of disulfide bonds in this electrode material for the battery that consisted of mixed sulfides, disulfide, and also had some particles oxidized by reaction with the electrolyte. So we had a little bit of everything going on in there. And also the samples were mostly very thick and self-absorbed, so we had to find the best behaved particles with the right amount of sulfur in them. And so this is the XAFS, and so in the fully charged state, you see there's a little shoulder in the XAFS here that indicates the formation of the disulfide bond, where this peak, the main peak is from the metal sulfides, and the peak to the left is from the oxidized sulfur from the electrolyte. So teasing all that apart, that was a pretty challenging experiment, but it could be done. So some of the challenges for the tender energy XAFS, you start with the facility requirements, what it takes to be able to do this in the first place. The sample environment is typically helium. Many samples are not vacuum compatible, so the atmosphere of choice is helium. About this much air will absorb your beam, so you need to have something more transparent around your sample, but that limits your sample somewhat. Beam motion during energy scanning is a problem for microbeam work, and it's more pronounced at lower energies because the monochromators have to travel longer distances and at steeper angles to reach those energies and to make those energy scans. So it's harder to achieve, but we've gotten that fixed in some locations. Energy calibration is also a key because you don't have the luxury you have at hard X-rays with transmission geometry, where you've got a reference, an energy calibration reference in line with your sample. Obviously, you can't do that at lower energies. So you have to make sure that the energy calibration is very stable for the beamline that you're using. And also, harmonics become a significant problem. As you go down in energy, you have to worry about the third harmonic of the silicon monochromator crystals. And the best example of that is I had a student several years ago who worked really hard at NSLS1 to make this measurement of phosphorus XAFS sorbed onto iron hydroxide. Because as you scan the XAFS for phosphorus, right about here, the harmonic hits the iron K edge. And so if that happens and you have a significant harmonic signal, even though you're windowing the detector, doing everything else with care, you're going to see a glitch in your data, an offset in your data. And that would be right in the middle of the XAFS that you're trying to measure. So you don't want that to happen. You really need to reject the harmonics even down to low energies. And that requires having mirrors in the beamline at fairly steep angles, like 10 or 12 milliradians, which is really unusual. So the test beamline was optimized for the harmonic rejection. So its harmonic rejection was better than 10 to the minus 5, which is really good, as well as calibration stability. So this was a measurement made at TESS on an iron phosphide at 2 micron resolution. So this combines all of the different requirements for a difficult experiment, and it succeeded. There are also experimental considerations. Again, the sampling depth is a consideration, so knowing where that is. But that also means that you can't have very much in front of your sample, such as using a really thin film to contain a sample if it's a powdered sample, or cover a sample to keep it from, to protect it. So you only use ultra-thin films for windowing material or sample covering material. Otherwise, it will just block the beam. Self-absorption is generally unavoidable in this energy range. In concentrated phases, self-absorption will be happening even with submicron particle sizes. So you can't get the particles fine enough to not have self-absorption. Even doing the standard approach of diluting a standard material, if your particle size is still larger than a half a micron or so, the individual particles within that diluted sample will be self-absorbed. And so you can't get away from it. It's actually hard, it's often harder to measure a good standard than it is to measure your sample for that reason. So that's, and it will vary with particle size. So it makes it harder to correct for. It's not like it's infinitely thick, then you apply a self-absorption correction. This is in between, it's always in between. So you've got a variable amount of self-absorption, even grain to grain within a sample. And so it's really hard to work with. You just have to kind of be aware of it and work around it wherever you can. There's also a fairly common problem with radiation-induced changes, especially to sulfur oxidation state, for example. At lower energies, more of the power of the beam is deposited right in the sample as you're analyzing it. And so you're more likely to have radiation-induced redox changes. And so brighter is not necessarily better, although the trend of facilities is to make things ever brighter and push the detectors to count higher count rates. I always raise my hand and say, that's not always best. Sometimes you really want to go the other way and optimize the detection of low signal and low noise measurements, because that's what you need to preserve your sample. A good example that we published recently was looking at sulfur in glass, and it was a hydrous glass. And the measurements were made at an undulator beamline at APS at medium intensity, and they saw the change go from one phase to another, from the first scan to the second scan. And they did the same measurement on the same sample at a even higher power undulator beamline at the Swiss light source, and they saw only the second phase from the first scan on. And then they brought the sample to TESS, and we made that measurement with really low signal and really low detection limits. And we saw that, in fact, it originally started out as a third phase. And at APS, it was already at the second phase before they saw it transforming to another one. So you kind of have to be really careful for photon-induced changes to your samples. So just be aware of that. Okay, and just to finish up, the last subject here is just some advanced approaches for heterogeneous samples. The first one is speciation imaging, where instead of looking at differences in the emission spectra, using the Zane spectra of the components that are in a mixture to map the distribution of those components. For example, in phosphorus, if you make one map at this energy and one map at this energy, then you can do some math and separate the contributions of each individual component to each pixel of a map. And so that's kind of a neat way of mapping the relative distribution of different species. And then integrated over an area of a map, you can then determine the ratio of those species within the map area. So I'll give an example of that. Again, back to the Ryugu asteroid. Although I had said before that the phosphate spots were all apatite, well, it turns out that not all of the phosphorus spots in the sample are phosphate. Some are phosphides. So we can actually map the distribution of phosphide and phosphate within an area of the sample by mapping it to energies and then doing the math. So this map shows the bright green spots are the are the phosphate spots, and the fewer but definitely there spots of red are phosphide, and that's an iron, nickel, chromium phosphide, which is a very interesting compound that's not found on Earth, but it is found in this asteroid. And we can map that, and by integrating the area, we calculate that 85% of the total phosphorus is in the form of apatite, and 15% is phosphide. And this has important implications for the formation conditions, the redox state of the formation conditions of this asteroid 4.7 billion years ago. So that's a pretty interesting result.
By integration, do you mean expanding the number of the grid itself?
Yes.
Number of
Basically, if you analyze the whole map, the integrated intensity of the phosphide signal, or the red, and the integrated intensity of green over the entire map. Since they were generated by the intensities of those, measured at those two energies, that actually does relate to concentration. There's a bit of a matrix effect that comes into play, but approximately it's that ratio. A more local geologic example is the sulfur speciation across a reaction front in a wellbore cement. So it was a cement lining a well used for geologic storage of liquid CO2 mixed with H2S. And that was pumped down into the well as a geologic sequestration type of experiment. But it reacted with the cement, and we mapped at 3 energies, and then recalculated the relative contributions of each species. So the red is elemental sulfur, blue is sulfate, and green is sulfite. And the reaction front progressed from the upper left to the lower right. So as the reaction progressed through the cement, it initially formed a sulfite, which was a metastable intermediate, and then that reacted further to form calcium sulfate and elemental sulfur, which is more stable long term. So again, this is just repeating the same map at three energies and then calculating out the results based on what we know about the Zanes. So we can map different species that way. And I've done similar work with actually up to 5 different sulfur species, relative distributions in a complex sample. So it's pretty useful. Okay, so the last thing I want to talk about is how to untangle spectra that are mixtures of species. So Zanes of mixed species are basically a weighted average of each species spectrum within the beam's footprint. And so options for separating those out include linear combination fitting or spectral feature analysis. I'll describe them on the next slide. But the separation depends on knowing the details about the potential components. If you don't know anything about the components that are there, you don't know what the mix is. So a good strategy is to use microbeam Zanes to find end members within a sample of the different components, and then use those components to interpret the bulk spectra. That's been done a number of times for a number of different elements very successfully. And you don't necessarily have to find an absolutely pure spot of one sample, but of one component. But if it's enough to identify what the components are, then you can say, okay, well, these are the components that are in my mixture, and then I can analyze where they are and how much they are. XAFS is also a weighted average, and so mixing, when you do a full XAFS analysis, data processing, you can mix in components from different models into that fitting process. As long as you're careful with the math and keep track of scaling of each contribution. That's doable. It makes it complicated, but it needs as much information as possible on the components. The more you know about the sample, the better. Then you can tease these things apart. And the interesting thing that I ran into with sulfur is that if the components in an XAFS spectrum have different oxidation states, you need to use very different E0 values for those components in your fitting model. So it can get pretty complicated, but not impossible. So getting back to Zane's analysis, comparing linear combination fitting with spectral feature analysis. Linear combination fitting works when you have really accurate examples of reference spectra of the components in the mixture. Typically, that's done for hard X-rays, and it works fairly well. But I want to caution everybody that it's often applied as a black box. Say, okay, I'll plug this into a linear combination fitting and get a result, and that's the answer. Unfortunately, that's often wrong. So have to be careful with using linear combination fitting. It's a very good tool, but just used with care. The reference spectra that you use for linear combination fitting should be measured under the same conditions, and especially at the same or similar concentrations. That's one of the keys. That's where it often goes wrong. Now, at lower energies for phosphorus and sulfur, it's even more complicated. Because of the fact that self-absorption is prevalent and it's particle size related, it's always there and it's always variable. So it's almost impossible to have exactly matched reference spectra. And the unfortunate thing about linear combination fitting is that peak height will dominate the fit. And so it's easy to fool it and get the wrong answer. So an alternative approach is SFA. Absorption and particle size effects alter the peak heights, but they don't change the position. That's the key. For phosphorus and sulfur especially, and lower energies, edges, the diagnostic features are the peak position and smaller minor features. Those are the diagnostic features, so you should concentrate on them and not worry so much about the peak height. So SFA breaks down a spectrum into its individual structural features. You dismantle a Zane spectrum into the edge step itself, one or more peaks resulting from electron transitions, and the start of the XAFS oscillations. So if you break down your reference standards in the same way, then you can reassemble those components into fitting for your unknown mixture and be independent of peak height issues. So this is a complicated example, but it's a good one because it was successful. This is a mixture of inorganic and organic sulfur species. So the spectrum looks kind of hard to interpret. If you just saw that spectrum, you wouldn't really know what was going on. But we know about this particular material that it has some, by using point spectra, we've known that there are some organic spots, there are some inorganic spots. We identified what the inorganic spots are. And for organic sulfur species, the feature characteristics are pretty well established from previous measurements. So we can use that. And these apply to general organic sulfur compounds, general classes of them, rather than specific compounds. So there may be 500 different chemical compounds in there, but you can classify them into organic sulfide, sulfoxide, sulfone, sulfonate, and sulfate ester species. And each of those species will have very characteristic peak positions and characteristics. So then you can fit the spectrum with components that you know come from known species, and then apply a scale factor appropriate to account for self-absorption, and you get a nice quantification of what's actually in your sample. And so this is really a powerful tool, and it's not susceptible to artifacts like linear combination fitting. And you don't necessarily have to know the exact chemical species and have a perfect spectrum of it in order to fit it. So that's a really powerful tool for analyzing mixtures of different species.
I wonder if it was ever compared against a known linear combination of known species, which like a physical mixture of known species, you know what they are.
Yeah, there's a paper, and I'm going to provide some references to upload to the webpage about this. One of them will be a paper by Prietzel et al., who did in soil science, they did a comparison between linear combination fitting and a form of spectral feature analysis. And their results were that basically the same thing I just said, that if you have really good spectra of your standards, linear combination fitting works better. If you have more variability or uncertainty in your compounds, which you often do in natural materials, the spectral feature analysis is a better approach.
Also, in harder transit, others use more objective methods for the component or not, and also the MCR.
Yeah.
That is not requiring the knowledge of references, but forms iterative spectral reconstruction of those references objects.
Right.
Have people tried to do this?
A little bit, but not so much. It's the limitation that runs into is again with the self-absorption. So you basically have to include in your modeling like 3 different degrees of self-absorption for the same compound, or the principal component analysis will find multiple versions of the same compound with different self-absorption. So that's a challenge there. I've actually helped people in some cases when they were insisting on using linear combination fitting to actually use a more and a less self-absorbed spectrum for each standard that they have for the linear combination fitting. And that helped a little bit, but I favor this method for sulfur and phosphorus because there's so many experimental variables. And for phosphorus, it's not spread out so nicely as for sulfur. So it's not necessarily as useful for multiple mixtures, but it is useful for identifying uncertain species. In different phosphate species, the peak position might only vary by or differ by about 0.1 eV, so it's really small. So the peak fitting gives you a better resolution of that peak position than simply picking the highest point, for example. And also it lets you resolve some of the smaller features. For example, in iron 3+ phosphates, this pre-edge feature is actually two Gaussian peaks. And SFA allows you to resolve those and confirm them. Or if you want to distinguish this from a manganese phosphate also has a pre-edge feature that at first glance looks about the same, but the actual component peaks are in slightly different positions. So you can use the SFA to distinguish between the manganese phosphate and the iron phosphate. So that's a very, it's a useful tool for teasing out the more subtle details that are important for phosphorus. So for sulfur, it's more of the broad brush, big details of what's where. And for phosphorus, the same tool is much more useful for teasing out the very subtle details, very small shifts of peak position and very small features. So that's all. Yes. And actually, one of them is fairly similar in position, but the other one is shifted over. So we've actually used that. If you have high enough quality data, we've actually used that to distinguish an approximate manganese-iron ratio for the phosphate. And so that's one of the more advanced uses.
Sulfur XAFS, we would find the approximation where you have a constant temperature factor for you, or the temperature factor of energy. Hard X-ray, people assume that the temperature factor for XAFS for any the hard X-ray. We're given energy.
Yeah, right. Yeah.
But then of course there is theoretical limit of energy even in hard X-ray, but everybody ignores. What about software? Do you assume constant S0 square or you better? Or you use some other?
I mostly assume constant, but I'm aware of the dependence. It definitely becomes important for silicon. So it's right in this range that it's becoming important.
What are the the lower the energy, the lower is the value of that. I don't know.
It's somewhat lower. It's generally somewhat lower, but not a lot. So just in conclusion, XAFS is a great tool, and it can be applied to really complex systems with due care. And the important thing is that the more you know about the sample, the better it is to constrain the XAFS, and the better your result. The more complex systems, the best approach is to break it down into its simpler components, and then just build it back up to its complexity. And if you look at problems that way, they can be solved, just step by step. But I do have to warn you that there are no easy shortcuts, and as the complexity of a system increases, the required amount of effort increases exponentially with that. So if you want to tackle some of these more complex systems, be prepared to work hard at it. But if it were easy, somebody else would have done it already. So that's science. So that's it.
Are there any more questions?
Well, back to where's a good example? Okay. The sulfide grains range from really big to really small, 100 to 200 micron size, or down to sub-micron sizes. So we see just a little bit of a difference in height, but not really significant. At the microscale, it's more particle size effects than matrix effects.
Kind of the same question. So, what would be the resolution? What's the status study decision? Or other, their hypothesis,
Right.
Answers,
Well, for the asteroids, these are the first samples of pristine material that we have been able to look at. that are basically preserved from the formation of the solar system 4.7 billion years ago. So the questions are, what was the chemistry 4.7 billion years ago before there were planets? And so that's a lot of unknowns.
There's also a question like based on like where it came from, from what planet broke away, or maybe it's just like.
Right. So the Ryugu samples, the prevailing theory after a lot of analyses, including ours, is that it formed as a protoplanet, so a small body that never made it into a whole planet. But it formed in the outer part of the solar system, in an area where it included some water ice and CO2 ice. And then as it accreted together in the early days of the solar system, there was a higher abundance of short-lived radioactive elements. And so it warmed up a little bit to about 100 C, warm enough to melt the ice. And the fluid percolated around it a little bit for a very short time. And that process altered the minerals and created what we see now. The other thing that's really of interest is that it also created some prebiotic organic compounds, even amino acids. And so these organic compounds, as well as sulfur compounds and phosphorus compounds, could have, because they were floating around the solar system, could have been delivered to the early surface of Earth and contributed to the formation of life on Earth. So that's kind of the big picture for what these materials are. And it's interesting that metal phosphides are used as industrial catalysts for complex organic compounds. So who knows? That might have been happening 4.7 billion years before somebody invented it on Earth. Yeah. Yes. Yeah. Some of this stuff is really low temperature geochemistry. We found, not me, not us personally, but researchers studying the Ryugu samples actually found sulfide grains that had inclusions of pure water. And they were very puzzled because, if anything, the fluid around there would have been pretty salty. Until I said, hey, wait a minute, what temperature did this crystallize at? It crystallized with inclusions of ice, pure water. So forming a mineral with inclusions of ice kind of it's not terrestrial thinking, that's for sure. So it's really unusual to think about the chemistry, the conditions under which this chemistry is happening.